Here's the solution to quiz number 8 for ECE 320 for spring 2022. The first problem is implement the following logic using NAND gates. To do that, you circle the ones. So here's a set of ones. I circle with the orange region or the red region. There's a one right here and one in the corner. I can do that by circling these four and those four. And there's a group of ones to get this guy. So that logic would be the green region is just B prime, the red is A, D, and orange is C, D prime. Now to implement that using NAND gates, I would just ignore the red circles for now. I would just do B prime ORed with A and D, ORed with C and D prime, then throw in double negatives. The AND not makes it an AND gate, not OR makes it an AND gate. And here I need to negate B prime, so the input is actually B. Or you can do B prime inverted, either way. That's problem 1. Problem 2. Implement the same logic using NOR gates. Here you circle the zeros rather than the ones. So here's a 0 right here. I'll circle it with these two. And here's 2 zeros, so I'll circle it with these 4. Again, the don't cares I can include, I don't have to include, it makes no difference, I don't care. Hence the name don't care. So that logic would be the red is B, C prime, D prime. The green is A prime, D, using De Morgan's law. With De Morgan's law, I negate both sides. Not Y gives you Y. And becomes or becomes and we'll flip the signs, so B becomes B bar, C bar becomes C. To implement that, that'd be B bar, C or D, ANDed with A or D prime. To make these NOR gates, throw in double negatives. Or not is NOR, not AND is also NOR. So add the red circles. That's problem 2. Problem 3. Find the voltages for the following DTL logic gate. In this case, I've got 3 inputs. Only one of them is on. Well, actually, not even that. To get these to turn on, I've got 1, 2, 3 diodes in series. I need 2.1 volts to turn it on. I only have 2 volts, which means all these diodes are turned off, and I2 is 0. The voltage at V1, everything's turned off, so V1 is floating. I know it's at least 1.3 volts, because otherwise this diode would turn on. It's less than 1.4 volts, otherwise these diodes would turn on. So it's something between 1.3 and 1.4 volts. I2 is 0. Again, not enough voltage to turn these on. That turns off this transistor. I now have the path to ground through here. The current is 10 volts minus 1, 2, 3 transistors. 10 minus 2.1 over 50K plus 1414 gives you 1.537 milliamps. To find V3, I can back into it. 10 minus I times R makes this 7.82 volts. And this transistor saturated, I've got 1.5 milliamps flowing. That allows 153 milliamps to flow. I'm only trying to push 10-ish, so beta IB is more than IC. This saturates. That's problem 3. Problem 4 is repeat. Now when the input is 10 volts, 5 volts, and 0 volts. In this case, I have enough voltage to turn on these diodes, and this will be max function. The 10 turns this on, making this 9.3 volts. This turns off this diode, turns off that diode. Only one diode can be on. They actually could all be off, like the previous problem, but if they're on, only one of them is turned on. So I have 9.3 volts for V1. The current is I've got 1, 2, 3 diodes in series. 10 minus 2.1 over 50K gives you 158 microamps. That allows 15 milliamps to flow, beta IB. I'm only trying to push 10-ish, so this saturates, making V 3.2 volts. 0.2 is not enough to turn on this path. I need 2.1 volts to turn these on, so this current is 0. And that turns off the transistor. Then the voltage by voltage division is going to be R1 over R1 plus R2 times 10 volts. For me, when that was 1414 ohms, 9.75 volts. Problem 5 is open collector logic. Let's get this out of the way. So over here I've got 0 volts. I need 1.4 volts to turn this on. That's not enough, so all these are turned off. Over here I've got 10 volts and 0 volts. The 10 volts turns it on. This guy turns off. So I've got 10 minus 2 diodes, 10 minus 1.4 over 50K, 172 microamps. And here I've got 2. I'm not really sure which one's turned on. They actually won't both be turned on because if this is just a hair larger than 0.7 volts to turn on voltage, then the bottom one turns on. One of these will have a slightly lower turn on voltage, and that one wins. From our standpoint, it really makes no difference. The net result is this is 9.3 volts, 0.7 volts, 10 minus 1.4 over 50K is the current. And then the current allows 17 milliamps to flow, allows 17 milliamps to flow. I'm only pushing 9, so these are saturated. The other 9 is going to split up. Regardless, beta IB is more than IC. These are saturated. V4 is 0.2 volts. And the last problem, find the voltages for this TTL gate. And here's one we haven't really covered yet. Got 3 inputs. These are 3 diodes. The voltage drive is V1. Drive the 10 volt, 5 volt, or 0 volts. So this is a min function. 0 volt wins. Kind of figure if this diode is turned on, I'll have, well, I don't know. If this diode is turned on, I'll have 7 volts. That's too much. I can't have 0.7 volts across the diode. So actually this one turns on and the other 2 turn off. So this is 0, that's 0.7. The current then is 10 minus 0.7 over 100K. There is no current over here, so I4 equals 0. If there's no current, T2 is off, and then by voltage division, I have 9.86 volts. The voltage of V2 is kind of unknown, it's floating. It's more or less than 0.7, because if I have more than 0.7, this diode turns on. It is more than 0, because otherwise this is 0.7, this diode would turn on. So something between 0 and 0.7. So that is quiz number 6 for ECE 320.